So I've illustrated this technique of complexifying a problem with an integral and making that integral easier. The reason it's easier is because derivatives and integrals of exponentials are easier than sines and cosines, right? So if I need to integrate e to something, that's usually a lot easier than integrating a sine, because sines and cosines mix up together when you take the derivatives or integrals, but the derivative of e is just e, right? Okay, so let's do this same thing again, and let's move back to ODEs. So I want to go back to this kind of problem where I have an ODE, inhomogeneous ODE, which has a cosine or sine on the right-hand side. And we'll illustrate the same kind of technique of complexification as a way to make it simpler. So let's do this example of an ODE using complexification on an ODE. So I've got an inhomogeneous ODE here. And the right-hand side is sine of 2t. So this is the case that's going to be of most interest to us. Sine of 2t. So my goal now is to use that complexification to get the sine in the form of a complex exponential. That will make my life easier because taking derivatives of a complex exponential is easier. So I'm going to take, I note that sine of 2t is the imaginary part of e to the 2it, because e to the 2it is cos 2t plus I sine 2t. So the right-hand side is the imaginary part of something. If the left-hand side was the imaginary part of something, I would have an equation which would be, I could get my original equation back by just taking the imaginary part of both sides. So what I'm going to do is take a complex variable z is going to be equal to x, which is some real function. Well, let's make clear that it's a function of t. Z of t is going to be some function x of t plus I y of t. So I notice that y of t is the imaginary part of z of t. And then I have a complex ODE as follows. Complex ODE is z double dot plus 3/2 z dot. This part looks the same, plus 5z is equal to e to the 2it. If I take the imaginary part of this side, I get y double dot plus 3/2 y dot plus 5y. And if I take the imaginary part of this side, I get sine of 2t. So my original equation is the imaginary part of both sides of this complex equation. So my plan is now to solve for z, which should be easy because I've changed it into exponentials on this side. And then at the end of the day, I will take the imaginary part to get back y. Okay, let's solve it. I'm trying to get a particular solution. So I'm going to guess z is equal to some constant times e to the 2it. And a could be complex. Let's plug it into the ODE. And that's what it looks like. I have a 2it in every term. And let's see, where can I go here? Let me go up here. So what I get out of this is minus 4 times a plus 3ia plus 5a equals to 1. And so out of this I get a is equal to 1 over 1 plus 3i. So I was able to find a particular solution, which is this one, by guessing a e to the 2it, by matching this side, because that side is an exponential. If I have e to something, I just guess e to something times a constant. and the constant turns out to be 1 plus 3i. So that was pretty easy to find that particular solution. So I made it easier by looking at the complex ODE. But we're not done yet, so now I have to do step 3, which is to go back and find y. Okay, so we're working on this example. We're trying to find a particular solution to this equation, which has a sign on the right-hand side, so it's inhomogeneous. We made a complex ODE, which is this one here, and I get the original ODE, which I'm trying to solve by taking the imaginary part of the complex ODE. And so that means y has to be the imaginary part of z. So if I can solve for z, and then take the imaginary part, I will have y. And I think this is easier than solving for y itself, and I'll show you why. So we just figured out that on the previous slide that it's very easy to find a particular solution for z, and that's what we found on the previous slide. So that part was trivial, really simple to plug that in. Now the only hard part is I have to go back and determine y. So determine y, which is the imaginary part of z. So 1 over 1 plus 3i e to the 2it. Okay, so taking the imaginary part is a little bit tricky. We just have to do some algebra to write it in the form of a real part plus an imaginary part. So I expanded out the exponential in terms of a real part and imaginary part using Euler's theorem, and then I multiplied that fraction out front by its complex conjugate on the numerator and denominator. Okay, so what do I get here? Imaginary part, here I have 1 minus 3i. The denominator is 10 times cosine 2t plus I sine 2t. And now group together the real parts and the imaginary parts. So I expanded it out and collected all the terms that have the I in them. So here's the real part, and here's the imaginary part. So that means since I only need the imaginary part, I've got yp of t is equal to 1 over 10 times sine of 2t minus 3 cosine of 2t. So that's pretty slick. That's a tricky way of getting this particular solution by finding this particular solution to a complexified ODE and then taking the imaginary part. And we're going to use this trick when we go back to physics in the next lecture. This technique of complexification can be kind of tricky the first time you see it, so here's some extra practice. These are things that are useful, like sine of, let's start cosine here. The real part of e to the I theta, of course, is cosine of theta by Euler's theorem, and the imaginary part of e to the I theta, of course, is sine theta. But sometimes maybe you don't want to use, if you have cosine, you maybe want it to be the imaginary part of some function. If you have sine, you want it to be the real part of something. So that's easy to do just by multiplying by an I. The real part of I, e to the I theta, is equal to what? That's equal to minus sine of theta. And the imaginary part of I, e to the I theta, is equal to cosine of theta. So here's some extra practice. So suppose I had an ODE which had this function on the right-hand side, a combination of sines and cosines. How would I handle it? Well, first I would try to complexify it. So f of t can be written as the real part of what function? So for this, I'm just going to use this equation here. I'm going to write cosine as the real part of e to the I theta, and I'm going to write sine theta is the real part of minus I e to the I theta. So I'm going to have here f of t is equal to 3 times the real part of e to the 2it plus 5 times the real part of minus I e to the 2it. The minus sign there is this minus sign. So I replace sine of 2t with minus the real part of I e to the I theta, or I e to the 2it. And then I can pull that out, the real part of this whole thing, 3 e to the 2it plus minus 5 e to the 2it, which is the real part of, and I missed an I, minus 5i. 3 minus 5i e to the 2it. Okay. So there's an example of complexifying something which has a cosine and a sine in it. And if you want, you can go ahead and check, double check. You can expand this whole thing out. And that's what I did in notes. So you can double check that this does in fact work. Okay, and then I got one more sort of take-home exercise for you to do on the next slide. So here's some extra practice for you. Suppose that I had this on the right-hand side of my ODE, 2 cos 3t minus 7 sine 3t. Maybe I want to write it as the imaginary part of something. So I'm going to complexify this f into some complex function, and I want the regular f, this f, to be the imaginary part of that function. Which of these would be a good choice for my complex function? So go ahead and try and work it out. Work it out yourself, and you can always check it by taking the imaginary part of all the choices and seeing which one works. So this I'll leave as an exercise for you to finish. And then otherwise, I think we've demonstrated how to solve these inhomogeneous ODEs using this complexification technique. So now the next step is to apply this to a physical system. Let's go back to the harmonic oscillator again, and we'll use these math techniques to analyze that system.